Right, welcome everybody, day 40. So, let's get into it right away. There will be maps, and if you just browse in the YouTube stuff and you watch the first 2 minutes of video to figure out, am I interested? Um, this is gonna be 99% about maps and how to explore and all of that. Usually it's a popular subject, topic maybe I should say, and let's do it. So the background story of these, let's see if I can do it. Season 1, episode 40, is that I was saying I'm gonna I'm gonna quickly polish up the scene and finish symmetrizing the rig again, and then release the scene. And then I bumped into a bug with the foot. So I was doing a stream, which was a chill stream, just to get stuff back in order. Bumped into it, decided not to keep that as an actual public video, and I certainly didn't want to do work that actually affects the rig off screen. So yesterday I was thinking about this, and I was like, oh, maybe it's been a while since we've done a math stream, and maybe I should go over it again. And it's about rotations and how they relate to vectors. And then anyway, train of thought kind of ran over me. I was like, oh, maybe I should explain these and that. And by the end of it, I had a pile of things I wanted to talk about. And I was like, I gotta do a stream. I decided this morning, so short announcement time and all of that. That's why it's early here, so there will be some drinking of coffee. Hopefully, it's not too annoying for you. Now, I don't know if we're gonna get to actually changing the rig at all. But what we're looking at is that when there's this heel back motion, you can see that the mechanics here work just fine. So the actual mechanics of the foot roll are rolling backwards on the heel back the way they should. But the way they're transmitted down to the actual foot, you can see that past a certain point, so I need to go backwards to show it. Past a certain point, it looks like they're reversing. So, and if you observe what it is, if you've been rigging exactly the way I have, or you have one of the older scenes, because this has been there for a while, there's a vector here, which is the Z1, that we're measuring the angle of our foot. So this item here, the foot roll, we're measuring the angle between the vector derived from these and the Z vector, and using that angle to roll the foot back by applying it to the displacement. Now that angle is not signed, and there's ways to do it. So, well, obviously there are, because we're gonna fix it at some point. But then, questions about vectors or rotations and so on keep coming up, and I thought I'm gonna do a stream about it. So, the maths. Now, there's one thing that I reckon is what I want to get out of this stream, which is how you learn maths, if you will. And there's a pretty important process which is often not formalized. And one of the reasons that at school people don't realize that they like maths, and that has ruined maths for some people for life when they could have been pretty good at it, is that there's a natural process the way most people, unless you're some synesthetic genius, that goes, you have an intuition, you find an application, you formalize that, you prove the formalization, and then you reapply the general model. Now, the way maps is often taught is that they look at the historical record of what exists. So they start from a bunch of formalizations and they say, hey, here's something that some very smart dude somewhere said. Just take it for granted. Here's the proof. And by the way, learn it off the top of your head, memory. You gotta know how to prove this formalization, regardless of whether you actually understand it, or you've internalized it or not, and then show me that you can actually apply it. So this completely misses this, which is probably the most important part. And the reason why a lot of people come late to maths and figure out that they like them late in their life, especially when you do graphics or something like that, and like this has been heard a million times, I'm sure quite a few of my viewers can relate. They go like, oh, if only I had seen the CG stuff when I was in school, I would have paid attention. And what is happening there, and this is my take on it, but I'm sure quite a few people came to exactly the same realization and probably a very similar way to explain it, is that you are in a sort of in an exploration stage. You obtain an intuition by observing that certain things behave a certain way. You start applying it, you find wholesome fallacies in your application, but there is some intuition under there that is working for you. And that's when you start looking up on Wikipedia, you know, what is going on with this, what is going on with that, and you start looking at the formalization of something. And then proof is something that people that learn maths in that intuitive, explorative fashion often skip. Normally, what they do is they kind of loop this part, they short circuit the proof part, and they refine their application and their intuition, but they'll never get to knowing the real formalization. And that is perfectly okay, for the record. That can get you a very, very long way. And that's how a lot of the people in the VFX industry and game industry actually know maths, you know, before it comes to a certain level of technicality, I guess. So at this stage here, there is something that is often missing, which is this arrow getting from one to the other. And a lot of these, it's not like you always proceed in this fashion. I mean, any of these arrows, any of these stages often requires that you iterate several times, where you refine your intuition by applying it and tweaking it. This is an exploration stage. And whatever you do, if you actually care to learn how the numbers behind all of these work, facilitating that, which might mean, you know, paying your dues, paying the entry fee of learning some scripting, learning to use Jupyter plus Python plus R or whatever, learning to use Desmos and so on. If you facilitate that feedback loop, which is basically the length of this transition for you and how many times you can do that transition, that is where you start learning exponentially faster than you were before. So that's basically what this video is going to be about. I'm going to pick a couple of subjects and try and explore them, or show what an exploration of that subject and what tools you can use to explore it will look like. Now, this is a longer introduction than I wanted, but I kind of wanted to get that off my chest. So we are going to look at rotations, and there's a classic thing that scares the hell out of people, so we're not going to go super deep in these, but one of the best pages of the documentation in Maya is the M transformation matrix one. That one tells you how rotation actually works. And rotation is probably one of the most misunderstood and misapplied things that there is in general in rigging. And it's a tough subject. You see it as a very primitive thing when you're animating or when you're rigging things in Brownian motion kind of fashion, by just connecting things and seeing what works and what doesn't. Those three numbers in an Euler rotation are actually really nasty to deal with. Rotation is never a trivial thing. And there's a bunch of things in the formalizations that we're not really going to spend a lot of time on, but one of the things that makes it very nasty is that coming from algebra, which is where most people develop what little knowledge of formalities they have, you might be used to things having a lot of nice properties. That's why algebra is one of the first things you teach right after arithmetics, like basic arithmetics. Because you have all kind of convenient properties. You have commutativity, practically every operation is commutative, other than division. You have associativity. There's a bunch of things that make it really easy because you can shuffle the numbers, you can explode and decompose and recompose things very trivially. Once you start getting into something like rotations, a lot of that goes out of the window. Even just adding two things when they're fields of numbers becomes a lot harder. So one thing that I recommend people spend a little bit of time with, just for the sake of exploring and understanding what is going on, is Desmos. Now I haven't been using it for a bit because I've actually bought Mathematica, which is pretty tough to use. It's still not friendly at all, but it can do a million interesting things. But if you're a beginner explorer, whatever it is, this is a really good place to start. So Desmos.com, you don't need an account or anything. You can even share graphs and practically anything. Start from there. Now I hope that this is actually okay. So yeah, I hope it doesn't challenge the codec too much. So chat, how's it looking? Is the grid murdering your viewport or whatever? So anyway, while I wait for that reply. Now there's a couple things to learn here. Now one of the things we work with the most is vectors. And the thing that is tricky about this is that you're used to working in an imperative fashion. Fine, and then here, cool. You're used to working in an imperative fashion, which is something akin to going, okay, I have a vector, I'm gonna say that I got P0 and it goes that far, so that means it needs to reach some P1, and you give these numbers, right? And I don't know, whatever it is, this is gonna be 0, 0, 0, and this one is gonna be whatever it might be on the y and x. Maybe it's 4, 2, 0. It doesn't really matter all that much. So right away you have numbers in there. Okay, and that is one of the things where you find that the formalized part of mathematics is really in conflict with the way you're used to operating. Because a lot of what you see in maths is supposed to be stating the general case, which is why I was kind of harping on to this general model thing. So something as simple as drawing a circle, you might take it for granted as a primitive, but as a function, that is very different. So that is where you go, okay, how do I draw a circle in something that requires that I express mathematics? And that is where you gotta learn some of the formulas, but that is where a lot of the formalization comes into play. So Desmos is pretty easy to use. At the same time, if you work in an imperative fashion, it's gonna fight you every step of the way. So what is it? Man, I don't even remember a lot of the formulas off the top of my head. Okay, I'm not doing super bad. So if you want a circle, now this is what's called an equality, right? X caret, the caret character is, I don't know if I can, because you'll immediately interpret it as an exponent. So let me get a notepad. So this is something that if you've been writing code, you will know. That's basically how you express a power. Now, to draw these, what is basically happening is you're saying, if I go down in x by any amount, when is that equal to 1? And you will get this point, right? And you see the intersections. Desmos is going to show you these as intersections between interesting things and whatever formulas you have. Now, when I go up the y, when is it going to be equal to 1? So this is a case in programming terms where you're saying this is true. The x squared equals 1 and y squared equals 1 when you're on the 0. Why? Because if you do something like, if you look at something like this, when x is 0, y squared is going to be equal 1, you're going to get that. And if you want the radius parameters, that parameter, that's going to be squared as well, but we'll look at that later. If your y is 0, so you're going down this line, the intersection is at 1. Now, if you're saying that the two added together must be 1. That might start looking familiar. So if you think of this as your third side, that's pretty much Pythagoras theorem, right? So for anything such as that, and that's why you have all the squares. If you remember, if you take these two squares and you sum their area, their surface, you obtain this square. So if you get the square root of that, then you obtain this side. So you can see where relationship between different things start forming. Learning to express things this way is actually pretty useful. Now there's a thing where if you type just r equals 1, it will get you a circle. So you'll find all kinds of shortcuts in Desmos like this. Some names are gonna be reserved because they're constants in maths, like E is one of them, R, I don't think I is, and some of them you can take over, whereas some of them will instantly trigger something like if you do F, it's not gonna let you use it as a variable because that is what functions are indicated as. But anyway, and you can't use long words. Bit of a bummer, but not too bad. So the other thing you can do is actually give it a number or a letter, and you get R1, R2, and so on if you want them. And that is not going to be shortcutted. So if you do something like that, then that's the same equation. And you can see that everything is squared. So if you had square roots on both sides, then you will get exactly Pythagoras theorem. But by stating that they're identical, you're basically saying, I want the equation for a circle. And then all kind of algebraic properties come into play, where if I move that on the other side and leave a 0 here, it's the same thing. So that's the part where you go, like, if you actually want to start playing with the operations and all the things that you forgot that you learned in, you know, anywhere between middle school and early high school, like, this is a great place to do it. Instead of doing it on paper, which is still a good exercise, these can help you a lot. Now, next thing we want to talk about, because it's going to be kind of important. And by the way, maybe I should have started with that. This is going to be a mishmash, like this stream is going to be a mishmash of a lot of stuff. It's all kind of thoughts that occurred to me before doing it that I thought, oh, okay, if I want to get, you know, to point B, I got to go through A first. And then, oh, actually, that's not point B, it's C. I got 3 things to explain. Anyway, now other things that are interesting that you want to learn to do as soon as possible is you can add tables. And that is for visualization's sake. So these allow you to take variables in here. So if I want 2 points, A and B, what I can do here is I can do something like, so I wish I could do AX with the small x or A dot X, but I can't. So it's going to be a little bit confusing, if you will, but it is what it is. So A1 is going to be our X of A, and A2 is going to be our Y of A. Now, if you have something like that, you can also create a point by saying A1, A2, like that, and you get a point, and it's movable. So it affects these backwards, actually. They can both affect each other. And that is actually really, really useful. So this is our 0 vector. I don't believe you can name points, but it doesn't matter, because at this point I've named the individual coordinates. And this is just a manipulation / display thing. So you can rig in Desmos. Now, in here, as the first part of the table, I can at this point do A1 and A2. Now, the next thing we want to do is also get ourselves a B. So B1 equals 0. Stop me whenever this gets too boring, chat, or ask questions or whatever. But my objective here is informing the exploration stage. So hopefully, like, if even just a handful of you start picking these up and playing with it, mission accomplished. So this is a way you can place a couple of points, right? Now you could also choose to make it not movable. Now there's a thing you need to know, there's no right click because that's taken over by the browser. So whenever you're looking for a right click, hold your click. That's pretty much it. You can turn drag off, and that means that you can't manipulate it anymore. We want this to be our 0 point, so we'll do that. And you can set ranges for the slider. So all of these should be reasonably familiar, I guess. Purple, not a great color, but whatever. And now, oh, because it's showing me the point for the table. No, that's in black. Anyway, it doesn't matter. So B1 and B2. Now what I have here is a table. You can, again, hold your click, choose lines, turn off points. You could choose to have drag, so you can hide those points if you want to, and make them draggable from here, but we're not going to do that because we want to constrain the manipulation. And at that point, congratulations, you can now draw the contents of your table. Now this is where things can kind of get a little bit more interesting. Because what we have now is something that can draw A and B, okay? This point is completely useless, and you can have notes and stuff. Because we're not manipulating it and we're accessing the coordinates, but whatever, you know, you can use it for visualization. That way you don't need to turn points on here, make these, you know, dash, whatever, so that it's less confusing. And there you go. So this is the other part where if you're trying to visualize trig, and Desmos is for the most part 2D only. I mean, visualization wise, it is what it is, but a lot of problems that work in 3D can actually be reduced to 2D just fine. So now if you remember, we talked about it. We've talked about the unit circle a fair bit. We might want to control the position of this B point. So, oops, practice what I preach. Hold the click, which is a little bit harder than it should be on a tablet. Now, if you remember, we say that as you progress down this circle, and we're going to use the same conventions we use in Maya, so it's from y0 and x1, we're going to go counterclockwise. Proceeding in this direction, your sign is the one that increments. So here your sign is 0, and as you go up, here it's going to be 1. So if we took this point and we said its y coordinate to be the sine of an angle, we should get something that sits on that circle. So let's start by getting ourselves an angle. I believe that, nah, can't range theta. So normally Greek letters are used for angles and you can do a bunch of stuff with them, but anyway. You can type things like pi, so we could say this is going to be from minus pi to pi, which is the periodicity of most trigonometric functions. Or if you want to loop around, you could go, it goes from 0 to 2 pi, and that's going to be our full circle, basically. So we move that up. And then we can go, okay, I would like this B2 to actually be the sine of alpha, and you type alpha and it will eventually resolve it to that letter. So you can see that the point is now sitting there. Now the cosine is the opposite. At this point, when the angle is 0 and our angle is going to be proceeding this way, remember that, the cosine is going to be 1, so which will place the point here. When you're going to be up that way on the angular momentum, the cosine is going to be 0. So it is the intuitive option, as well as the formulaically correct one, to set the z. So to set the x, sorry. Now, that point there, B1, B2, it's become useless, so we don't need it. So there you go. Now, as you increase the angle, you're pretty much doing your rotation on a plane. So this might seem like a triviality. It kind of is in many ways, and we could set this point to be the same if we wanted to draw that end, or we could actually, let's turn points, oh come on, turn points on here, make them non-draggable. But this is pretty much the main thing that you care for when it comes 2 rotations. Now the other part that you're interested in, and these might start looking a bit like matrix, and we'll go over that as well. The other thing that we might be interested in is going like, okay, that looks a lot like what our x-axis should be. So let's go for red. Let's make the circle black, whatever we consider it background. Now, if we wanted the y, we have a behavior that's not too dissimilar. Now, I believe you can copy and paste to, no. I believe you can copy and paste tables, but I don't remember how. I'm not sure. So I'm going to create a new one. Bear with me. So that is going to be our x-axis. Again, mishmash of everything. So if you're going like, this doesn't make sense, it is the way it is. I'm just going over a bunch of things that popped into my head. Now, you kind of want to do something which is the opposite, where you want to place, when the rotation is 0, you want to place the y, the endpoint in y, at 1. So that means that in here, you have the cos alpha, and in here you have the sine alpha. Now the other thing I would like to do, if that's even correct, come on, I gotta use the mouse for this because the tablet is killing me. No, unless I'm stupid, sorry, that's, I am an idiot. It's, see, I'm a complete idiot because I swapped two things that don't have that kind of relationship. It is the cosine of pi minus alpha. Doesn't matter how many times you do it. Okay, better. So this should now be sitting at 90 degrees. Doesn't matter how many times you do it, it still never gets any better if you have terrible memory. So why am I stupid? I need to think about this for a second. Minus sine alpha. So this is, let's actually look at the, I'm really idioting out here, but it's actually going to be minus sine alpha for the x. And yeah, so this is the part where you can look at the rotational part where you go ax, ay, and az, and you can see that it's minus sine and plus cosine. So this is the table that we're composing basically, right? Sorry for the mishaps. I was off the cuff and it didn't work out. But that's why I'm saying that your intuition is normally good. If you can experiment a little bit, you'll find that you're just thinking of the wrong direction or something like that. So minus sine alpha cos alpha, yeah, there you go. Is it still making sense, chat, what we're going through? So there you go. All right, now, I think that when we did the trig and vector videos, I actually went over these, but what we're basically doing here is transforming, it's a frame transform. So if you think of your transforms as individual components, which they are for the record, affine matrices, which is what we use a lot, are pretty much just an artificial kind of thing. This is what it boils down to. And your intuition might be that as you progress, okay, Windows just beeped. I don't know why. Save changes. What? Sure, save the changes just in case. I didn't want you to quit or anything. So your intuition here, and the reason why you should get yourself means to experiment as quickly as possible, is that you go, okay, I'm a 0 here. Then as I progress through the circle, you know, it's going to go like that. But the reality of it is that while your visual intuition might be that, this number is actually sitting on a completely different you know, on its own number line, and it's progressing that way from 0 to 1 and then going back to -1 and so on and on. And that's the periodicity of the function. So you need to couple it, visually speaking, like when you actually are starting to correlate your visual intuition or your thinking, which is always going to be visual, with the actual numbers. Having something like this and realizing that these are composite operations is pretty important. And it's not super obvious, but you can find plenty of tutorials on the internet. This is the easiest way I found to draw lines in Desmos. Now, what happens when you do something like that is that you are basically creating a new basis in many ways. So normally you're saying this is the x basis and this is the y basis, and everything is explained and expressed in those terms. If I take those terms and push each of them through one or more transforms, something else happens. And in this case, you might think that this is just the transform, but what is really happening is that this is a vector and this is another vector, this is a point, so it's a displacement point, this is another displacement point, and you are putting those onto a new basis. So your transform expresses the fact that this stuff is moving around, and that transform is basically a base change. That's what a lot of stuff that you find in linear algebra and Sigrid papers that might seem indigestible to you, when they say we find a new basis and so on, that's basically why they say and what is happening. Because these are actually artificial items that need to exist in a space, they need to be moved to a new basis, and that's what a transform does. Right? So when you chain matrices together, very often like you could hear that expressed in, find a new base or find chain basis and so on. So that's pretty much it. That was just to get the term out there and explain what it is. Because people think that this is a transform. It's not. This is your transform, and it's expressed in a formulaic fashion, right? Now, we're doing this by transforming one of the two, which is the x, and the other one, which is the y. If we wanted a point which is going to be made of x and y to be transformed, we will need to get the x of that point transformed this way and the y of that point transformed that way. Okay? And that is where, hopefully, I don't know why I'm trying to switch window. That is where, hopefully, this starts making sense, right? So, and this is going to be hard to articulate, so I'm still going to try. Oftentimes, people hear that you have a matrix and, maybe they learn a little bit about vectors and matrices and so on. They go like, oh, I know linear algebra. And it's like, yes and no. So linear algebra is actually pretty vast and complex, and that's why some people say that what you're learning is vector algebra or matrix algebra, and even then you're talking of linear matrix algebra, because a lot of the stuff you do needs to be a linear transformation. But we're not going to talk about that. By the way, I mentioned it before, I believe, but there's a channel called 3 Blue 1 Brown that has amazing visualization videos for a lot of mathematical intuition, even for very basic subjects. Go and check it out. 3 Blue 1 Brown. Just search it on YouTube. It's pretty popular. Now, the whole thing with all these multiplications and so on is that there is an agreement, and I think we explained that when we're talking about linear algebra, vectors, matrices, and so on. There's that agreement in a certain field, much like there is in algebra, that if you take two terms, A and B or whatever you want to call them, and you put a sign between them, so you're saying, okay, I got A and B, you put some sort of sign between them, you agree on operating on those terms a certain way. Now, in the case of the number line, that is, and I can't draw a straight line to save my life today. It's the right day to actually suffer from that. So if you have your number line, and all the integers are here, but this is the reals, which are pretty much all numbers you will use in basic algebra. So you got infinite subdivisions here. Then we agree that saying that a plus b means taking a number that is here, let's say that this is a, and you have another number line. That's why I was saying this before. I'm glad I could actually look back to that. You have another number line. The two might not necessarily, visually speaking of intuition still, they might not be necessarily want to be sitting on the same one, which say is going to be sitting here. And this is B. There's an agreement here that basically says, like your visual intuition of this, that basically says, if this B were 1 here, right? A by B means that you will take this one and scale it out by that much. So let's say that this is 2.3 and this is 3.25. I should have taken integers, but whatever. Now there's an agreement where you're saying this one is gonna be now going that far, and then the 2 is gonna be going that far, and then the 3 is gonna be going that far, the 4 is gonna be going that far. Then you look at the number you had, and I don't know why I went that far. I didn't need that much, which is 0.3, so it's 3/10 of whatever you have here. And this is gonna be your new A prime. So its number is still the same, but its number line has been scaled. Then this number line becomes the new basis. So you project it down here. Now these are sitting on the same number line. And that is gonna be, have I used the same scales? More or less. Whatever, I probably completely overscale stuff. But anyway, that is gonna be where your result, which is gonna be 6.5, third of that, 7 and spare change. So I'm not gonna do the calculations, but you get the idea. So that is basically where that's gonna be sitting, and it's 7 and something. All right. Okay, they're all wonky. That's why they don't match. So that is the intuition of that simple multiplication. That's a visual intuition. And this is an axiom. So you're kind of accepting that you manipulate these numbers a certain way. And that's why a lot of stuff builds on algebra. It is a very, very axiomatic field. Now, linear algebra basically says that you can take a system, and that system can be expressed as a matrix, or rather, our application of linear algebra is going to say that. And if you have that system of n numbers, a field, whatever you want to call it, and you multiply, which is normally indicated with an x. So in normal algebra, in basic algebra, the dot and the x are usually the same, and everybody uses dot. But in linear algebra, it's almost always indicated with an x, almost. Now, when you do that, you're basically agreeing that you're going to be doing something like rows by columns, or columns by rows, depending if you're row major or column major. So you're going to do that. You're going to be do the multiplication. Then you're going to be doing the next on the row to the same items in the column. And you're gonna get your second term, so you get, you know, your 0, whatever we want to call it, 0 prime, and your 0 second from those multiplications, and so on. And that is gonna be your new number in here. So that's the way a matrix multiplication works, right? Well, I think we're being over that. It is not a bad idea to actually go through the practice of doing some of this by hand. It will consolidate a lot of things that when you're exploring are gonna help. And this is change number 1. It's just an agreement. Linear algebra states that we agree that if we run algebraic operations on the discrete items in two sets, they are going to be performed in a certain order, because the multiplication between two matrices done this way, if you run it the other way around, because there's this column row thing, it is not going to be the same. It's basically going to be a transposition. And you might have heard, or I might have told you at some point, that the transposition of a matrix is basically like taking its diagonal, which is not quite the determinant, but you know, it's affine to the determinant in many ways, and flipping it. So the basic idea of a transposition is that what was in there goes in there. Much like, I think the classic example that they use in school is take a piece of paper, a square piece of paper, if this is a square matrix, run a wire between two corners, flip it like that, that's a transposition. So because of the way you go columns and rows, or rows and columns, if you were to swap these two, it basically becomes the multiplication. Like, you will find that the result is the transposition of the first multiplication or whatever, but you start seeing that operations like the transposition on its own, which very often you might think doesn't make a lot of sense, the multiplication and so on, actually do correlate. All right, so chat, I really need your help here, because this is all off the cuff. Is it still making sense? Are you still with me? Now, moving on from that, there's a bunch of other things like transposition and inversion and so on. But one thing that we really want to get across here is that linear algebra works like that. What you're using, like the plainest form of it, the agreement between the parties, are those. But the way you use linear algebra in something like the Maya transformation matrix is actually not quite like that. Because the matrix as you have it in Maya is called an affine matrix, and it's actually two different transforms in a way. So normally, when you do multiplications like that, you get a certain result. If you run the, you know, something like an inversion in Maya, like a plane inversion, you will not get the right results. And that's because the Maya matrix, the blessed 4x4, actually is an affine matrix. It's kind of made of two transforms. So what it is that, and I wish I'd used a different color. I think this is important enough that I'll spend the time redoing it. So the Maya matrix is actually formed like that. I can do this. Yes, I can. This is where I really should learn how to draw straight lines with the tool. I know there's one, but I don't even know the shortcut. And that is actually what is called an affine transform. So it has two areas of interest, arguably three, but let's ignore that. Now, we've talked about homogeneous and non-homogeneous matrices, but let's ignore for a second this part here, and let's say that it's always, you know, the standard 0, 0, 0, 1, which means these are directional axes and this is a position and it's displaced by the magnitude that it indicates. Now, what is happening there is that this is going to be your y-axis as it's expressed, and I think I've mentioned all of these. This is going to be your x-axis, and this is going to be your z-axis. All right, so I'm not really trying to explain, because I've already done that to some extent, matrix maps here. I'm trying to get to the intuitions and playing with them. Now, I'm not gonna put so anyway, this will be your x of x. So this is the x value of your x-axis, this is your y value of your x-axis, and this is your z value of your x-axis. Hopefully that still makes sense. And this here is gonna be a displacement. It's gonna be your position, right? which is not an axis. That's actually, if you have word coordinates, that is going to be something that from those word coordinates untransformed or whatever moves you to some point in space. Then this one, in that transform, in that frame of transform, whatever it indicates is the one that draws this vector. It's indicated as 0 to say this is going to be normal, this is just a direction, don't care for anything else. Then it's going to draw in the y row, is going to draw you another vector. And lastly, you have the z1, which is going to get you hopefully an orthonormal, so orthogonal and normal third vector, which is the z. So this is what that matrix is actually expressing, okay? And the 2D version of it is going to be as valid as that. So this is a 4x4 matrix. Like square matrices have a lot of interesting properties which make them ideal for operations. Non-square matrices, you know, non-ideal in many cases for what we're trying to use and the way that Maya tries to formalize it to the users and so on. But a 2D matrix, everything that you do in a 2D matrix is perfectly applicable to the 3D matrix. Just you would have your rotation done in this space. So it's going to be 2x2 cells because you only need X here. We're using row matrices, which means the axis is going down that way. And your Y. And then you're going to have your X of X, your X of Y, and your Y of X and your Y of Y. Same thing as the as the one that we're talking about here. You're going to have some displacement for the two here. And in 2D space, which is a hell of a, and you're going to have just 0, 0, 1 here. Which is a hell of a lot easier to reason about. What that gets you is, okay, I'm going to be going to this point here, and I'm going to be orienting my x-axis that way and my y-axis that way. Now, if you want the ability to express any of these transformations, you need an operation. You need something that transforms numbers, not the numbers. Once you save it, you have your numbers, it will say this is the transform that has been expressed, and on some basis that was the preceding term or the following term or whatever. But the important part is that the transformation, the ability to go from one to the other given any value, so converting from angles in example to full transforms, is given by formulas like these, right? And because of the agreement between like the agreement specified by linear algebra or whatever, you can express those operations as a matrix of operations, and you say, look, if the multiplication works out that way, the terms are going to be the ones that are found in here. So a rotation around x, right, is going to be this. Now if you look at other things like rotation around z and so on, and there's an amazing video about dimensionality on, it's on Quaternions, but he discusses dimensionality on Free Blue 1 Brown. Might be a bit mind-bending, but the dimensionality part is pretty interesting. So if you want to transform something like a rotation on the x, you can see that our matrix can comfortably describe all of the terms that are in here, right? And you can see that this subset here is pretty much what we're going to be using here. So we're just kind of ignoring an axis because we're saying, and this might be a little bit confusing, but we're kind of saying at this point, in this case, hey, if we wanted to use that matrix specifically, it would be like if this was the y and this was the z and the x was actually coming out for shortening and all, but it was coming out through the viewer like that. All right. So all of this stuff, exactly the way we have been doing it. Oh, come on. Okay, exactly the way we've been doing it here is that, and nothing else. Now, trying to recollect my thoughts for a second. So that is basically the idea of the difference between a transformation and so on, and you know, use Desmos, play with it, figure stuff out. There's a lot to learn just from a few simple things, from things that you forgot from school, like equalities and inequalities, that you could never really figure out because they just tell you the numbers and they don't show you what they look like. 2D is a lot easier to reason about than 3D, because when you're working off a screen, like that third dimension has to be realized through perspective and so on, so you're already asking your brain to do a lot of interpolation. But a lot of the stuff works across the two. Now, I have done all of this work because I wanted to get to a couple of things. So I'm a little bit late compared to where I wanted to be, but we're still not doing too bad. Another operation that we might be interested in expressing is the projection of a vector. And we've talked about dot products and cross products. Do I want to hide some of this stuff? Probably yes. So we talked about dot products and cross products and so on. Okay, yeah, I can hide everything. Very good. I might actually just open a new Desmos. And how they work? Now, a lot of these operations work in in 2D and 3D, and a lot of these operations also work in between vectors and matrices, and that's one of the reasons to have square matrices and vectors of a certain size, is that if you have something like a 3D vector, and if you remember, we talked about it, you normally, to operate with these, you normally want the fourth term, and you can imply it, or you can express it and say that if it's 0, you're working on a direction, if it's 1, you're working on displacement, if it's anything in between, it's an interpolated displacement, whatever you want. But all of the operations we talked about work perfectly well to transform a vector by a matrix. So if you want to, and it's kind of what we've been doing, right? If you want to rotate one point and not a whole frame, whatever you're doing becomes much simpler, because the result of something like this is one single vector. Multiplying that vector by that matrix, pre-multiplying at least, is gonna get you a vector of the same size. And a lot less out of this becomes interesting. And again, that's what we have been doing here, right? So I can show this again. Don't need these. Because if you look at it, we have a subset. These A1 and A2 is just a 0 point, right? I could replace it with 0, 0, and it'd be just the same. Because the output you're interested in is much reduced. Same works for dot products and cross products. Now, let's get us a couple of vectors. This is kind of going slightly differently than I expected, but I do not mind it, I'll be honest. So 2 and 3, whatever, it doesn't really matter all that much. And can I? Yep, I can. So we make it draggable. Sorry, I'm trying to think about 5 different things. Because we can't get the tables, never mind that. It's a bad idea. So there's a reason if I was doing things a certain way before. So we're still gonna go A1 equals 0, A2 equals 2. For now we're gonna keep, what? And again, the point of this is half explaining these things again, because we did already. But the other half, which is possibly more important, is, hey, here's how you can play with some of these. Now, I do want to realize a couple points in these, so do I want a table? Again. Yeah, probably do. Bit of busy work here. It's kind of like, this is the noodling part, I guess, of these. Jadrees, hey man, have I seen you on stream before? My apologies if I have and I'm not remembering. If not, welcome. If yes, I'm sorry. So, what? Okay. For some reason this is, oh, okay, no, I'm just stupid. Yep, it's fine. Let me make them non-manipulatable. I have to rig these the same way I did the other. So lines, no points. Now I remember why I was doing things the way I did. Two expressions. So we're gonna go for one composed of A1 and 2 and another one composed of. I hope you're not crazy. All right, welcome to the stream. So now I should be able to comfortably manipulate. Cool. Now we've talked about the dot product and cross product, I believe, and we're gonna use red and green might suggest axes, which, yeah, it's fine. Doesn't really matter, does it? They're legible, so we're gonna go for it. And no points, thank you. So we've talked about dot products and cross products and all the such. Now we said, and this is an excellent way to play with things, because if you had to read this in Maya, it will take you a while, and it'd be hard to know, you know, what the numbers are and so on. Desmos is made to make that easier. You can label things, so you can label your results, which is pretty great. Now we say that the dot product is a representation of the relationship between the two magnitudes, right? And that is why it sits on the number line, and it's called the scalar product. Scalars being the individual terms of a field, and the vector being a field of scalars. Actually, I'm gonna take that tangent for just a few seconds because I forgot something important. When I was harping on, like when I was rambling about, talking about number lines and scaling the number lines and reprojecting and so on, one of the reasons why those numbers, the components of the discrete components of a field in linear algebra come down to that and are called scalars, is because of this. Because the basic agreement in fundamental algebra is, I think it's called essential algebra or fundamental algebra. In Southern Europe, it's often called Arabic algebra because that's where it comes from. That's where it comes from. That's why these individual components are called scalars. And the association of multiple components is often called the field. Sorry, mini tangent, but at least you know where those names came from and how to remember them. Now, the dot product is a scalar product, and it's gonna be on the number line, right? Because all it gives us is one value. So it seems pretty reasonable to express it as just one number. What do I want to call it? C, we're using A and B for points. We could just make it x equals something. So, and this is a part, okay, I'm gonna do it this way because there's something that I want to show. So if the dot product between two items is the summation of the product of each term by the others. So it should be, I forget about it, to be honest. I'm terrible like that. But let's make sure that we can verify. So if I set this one to 1, that's one of the terrible things about computers is they make you forget how to do things by hand. Even the most basic ones. It should be A1 by B1. Oh, because yep. Well, this is gonna be pretty easy because A1 by B1 is the only thing that actually does anything. Plus A2 by B2. So what is happening here? And maybe I want to fact check that before I lead you astray. It's embarrassing that I don't remember these. I have a mind blank on it. I'm pretty positive. Because it should be just that. Yeah. Cool. Sorry, I did not want to lead you astray. I felt like that was important to check. Now, that seems pretty convenient when you're talking about things like projection, because somebody the other day was asking me, you know, projections and rejections and so on. The thing is, it looks this nifty only if one of the two terms is going to be normal, which means 1. Because the relationship between these two lengths, the way the operations it's predicated on, which is one by the other by the cosine of theta, which is the angle between, and that is why you can basically use it to find the angle between two items. The relationship between these two is actually not linear the way you might imagine it is. So if I move this point, you can see that the projection of these gets non-linearly scaled by the length of that, right? You can see like it doesn't make necessarily a ton of sense. So what you need to do is basically, if you want something useful out of it, such as getting the angle, you normally need to normalize. Well, you will need to normalize one of the two. Now, is there a normalized? Nah, that's... So here's a nice thing, like if you start typing letters, it allows you to add sliders for things, because this is an operation n by o by r by m. So it goes like, hey, add sliders for all of these, but what I want is actually normalization. So, okay. I was hoping for something a little bit easier, but we can do it. Now, I think before I said you cannot normalize points. I don't know why I said it, because you can. Sorry, you cannot name points in Desmos. I was lying because you can, and I know how to do it, but I must have been thinking of something else. So if we have P0 and P1, we just name things. You can do distance, I believe. Yeah, you can call the distance function between two. So in this case, if we do the distance between P1, which one is which? So we want to normalize P0, sure. So if we do the distance between P0 and a 0, 0 point, we should get its length. And this is another thing I love about Desmos. It always instantly gives you something visualization-wise that's really useful, right? So now we have that. And if you remember, and this is a game where you can start like, it forces you to type out the things, and if you go through your exercises this way, you will remember so much more. Mathematica has a much more abstract and higher level set of capabilities, so it doesn't quite force you into these, and it's good because when you do the work that you can do in Mathematica, you know, you want that capability, but it doesn't force you through learning. Anyway, so we want to call this a R1 for ratio. Not a great idea, but, and we're gonna say that it's gonna be 1 divided. Now another thing you might want to know in Desmo is if you select something and you do divide, it will show you whatever divided by that, which is pretty convenient. And a lot of the copy and paste operations are taken over, and they will usually do what you want them to do. So we have our 1, which is this ratio. Now, if we take and produce another point, which is going to be P... Sorry, let me change the color of those things, because I'm confusing myself. Something serious, come on. So red and green. Okay, much better. Now I can read what I'm doing. Now, if we take Now it'd be cool to be able to do something like Pn, but it doesn't work like that. So we're just gonna go for P2, even if it's not a great nomenclature. And we actually compose it by taking both the terms of P0, which are A1 and A2, and multiply them by that. So we can do A1 R1 and A2 R1. Then you can see that we compose the point that is the normalization of this one. All right, chat, still with me? So this is kind of half lesson in Desmos, but remember the point of this is encouraging exploration, basically. Now, this dot product here, and this is the interesting part, you see it as this line, which will happen very often if you do things that are more complex, where you're interested in one value, or some equalities might be in the quadratic space, so they can produce two values, because the square root of a number can be both that like the positive and negative number of the same magnitude. But what it's really doing is saying, take this value x, you know, and make it equal to that, which means that the function itself is that at this value of x, there's the number, right? So the entire function lives on that point of x. It might be a bit confusing, you get used to it eventually. And this is pretty important when you start going into things like asymptotes and so on, where you need to express a line with a function, and oftentimes you see that being one number, and you go like, why, what's a one number function? What does it look like? It looks like that. Now, what we want is now gonna be so A1, P2, what am I doing here? Okay, so I can, one of the things, and it may be possible and I don't know about it, you can take P2 and do .x or something like that. So oftentimes you'll find yourself copying and pasting or making these equal to some variable and then pushing it in there. It's like, you're gonna run out of space reasonably quickly. But if that is P2x and P2y, then what we were doing there, oh come on, is the x of this point is what we want, and the y of that point by B1 and by B2 respectively. So this is the x, and that's kind of okay. And then because we're taking special cases, we want to take that and multiply it by B1, and take that and multiply it by B2. That seems reasonable. So verify things. If I move this close enough to 0, now you can see that this is basically projecting on the other. What you couldn't see before, I will need to make it a diagonal, which will be okay. But yeah, what you can see is basically that the magnitude we're producing is working out. That's great. Is it still making sense? Chat, I really need you to pitch in here, because, you know, I hope not to have lost everybody. I'm gonna keep moving on, but please pitch in. Now we've done all of this work, and we've expressed these. Oh good, cool. We've expressed all of these to say that from this dot product, we could actually obtain the angle between the two things, right? Now, the reality of it is that if you take something like, it's gonna generate, not yet, but it will generate the cosine of the angle between the two. So if you take something like the cosine function, it looks like that. It goes between 0 and 1. Now, the inverse function of most of the stuff in trigonometry, and these are transcendentals because they don't resolve to a polynomial. You have to measure them, basically. That's the way they work. They transcend calculation and they can only be measured. That's how we know sines and cosines and so on. There are approximations if you want them in some computable form, which is what your sine and cosine functions in libraries do, but they're always approximation. Now, the inverse function is going to kind of look like the same, but like it's going on that axis in a way. Or you can think of it that way. Now you can do r cos of x. And if you imagine that going that way, you can probably see what I was talking about. There's a number of interesting things coming with it, but we're not going to go into that kind of transform yet. But the interesting part to you is that this starts at -1 and ends at 1. And we've talked about it, but that is the domain of the function, right? So another thing that I think is really useful in going through these exercises is play with the functions that you're using. Figure out what the relationship between space and the domain of what are, fundamentally 1D functions, which you need to add one dimension to visualize transformation. They're great. It gives you such a, if you start remembering some of the shapes, it gives you an understanding of what is going on. Now, something like that means that whatever we're doing here cannot exceed that domain. But the relationship between the two, like we've kind of already demonstrated in a way, that the relationship between the two sort of works out pretty well, even if you actually rescale these things. So if we scale both to be normal, then that is actually gonna be giving us, like if both were normal, and this is why, I went through so much stuff here. Let me add. Oh, come on. What? I am keyboard blind. If both were on 1, right? And this is, again, sometimes you figure out, something and you don't know why it works. Whoops. And you don't know why it works, and, you need to develop the intuition into a formality. If both of them were 1, you can start to see that then they basically always, because these are just directions, they cannot be anywhere, they always sit on the unit circle. And that's where all those relationships between these products and angles basically come from, right? Now, let's see how long it would be going for. Not too bad. I reckon we can get to where I wanted to. I mean, this is dragging on, but I think it's an important enough video. So if we also normalize the other point, which is P0, and we have P2. Fair enough. Let's go for P4. Sorry, P3. Not super fond of these, but P3 will be the normalization of B. So we can actually. What is it? Where was I getting? R1 was the ratio, so I need an R2 as well. Is this starting to feel pretty similar to rigging, where you start juggling with the software that's not quite designed to be as complex as you need it to be? Because I'll admit it is to me. It is feeling that way. Rigging in Desmos. But it is a great exercise. Please take the time to do it if you have the inclination, if you care about maths. So what we want to swap here then becomes, oh, come on, B1 by R2. And this is why I was saying I'm not fond of the names, because you are treading on eggshells here. So now I have the two vectors normalized. We're doing great. We actually are. We're not doing too bad, are we? Now you can see that whatever you do between the two, they're going to be sitting on the unit circle. So all of the operations we talked about, with those multiplications in the dot products and so on, if this is, and the whole point of why I was, rambling about bases and so on, it's kind of building up to this. If you multiply these two, it is not different than this being here. So it's your new basis, and this being here. So if we run the dot product, which is multiplying the terms, it becomes very, very similar to one of the properties, the SOHCAHTOA properties, that you use, you have the Pythagorean theorem to deal with the sides and so on. But one of the properties is that the cosine of this angle is also related to those lengths. If you have the sides in a triangle, and this is a rectangular triangle, you know, you can get that. And that's where the dot product comes from. So when you do that, and this is the new basis, so when you do a dot product between two normal vectors, what you're obtaining is this one in the base of that, which happens to express the cosine of that angle. All right? Still making sense? I hope. It was a question and I phrased it like I toned it like a statement, pronounced it like a statement. Anyway, so now if we do the dot product between those two, which is going to be, like here I was getting away with murder. Now I need to be doing, let's actually recycle these because this is kind of useless the way it is now anyway. We want to do, no, why? Don't do that to me. This is x of a, which is given by those two terms. Look at us. And this is why I love doing these things in Desmos. Like, and I constantly, partly for the stream, but partly because I like it, I constantly go through the basics over and over again. These I might want to call P3. It doesn't care about the name. That's the thing. It's just for our clarity because you can't access it anyway other than in things like distance and so on. So this is going to be the x coordinate, which you can see if this was, you know, projected on the 0, it boils down to pretty much this simple operation and it gives you the x coordinate. Let's see if I do this right. Multiplied by this plus the y of x multiplied by the y of y. And you don't need this asterisk I'm putting here that gives us the dot, you don't need it. So here's the other thing that I find interesting. Like when you do it like this is one of the other constraints of Desmos that, you know, constraints are good for learning sometimes. It shows you how all of this stuff you're doing when you do dot products and you run all these complex things in your program as imperative sequences. When you're forced to do that in mathematical terms, eventually you find that maybe you don't need all those API calls to get the vector and transform it to something else and something else again, and then do a dot between the two and extract the one axis. Very often, like if you do just a little bit of work to rederive your stuff, you can reduce things to very, very simple scalar terms. All right? Now, what that is giving us is the cosine between the two. So it is at 1. Remember the cosine? You know, it's going to be at 1 when you're at 0, and it moves on and it becomes 0 when you're at 1. So we've just demonstrated the relationship between the dot product of two normalized vectors and the cosine of the angle between the two. Now, this is where things get interesting, because if you go through that, you can see it. Look at the number. Oh, the number here might be tough to see. And if I actually render it to an angle, I don't know how to render angles. I gotta be honest. I could probably do a. Anyway, let's not bother with it just yet. Sorry. I'll give it a label. See if I can. Can I do that? No, I can't because it's not a point, is it? Anyway, sorry, bear with me. But yeah, you... I'm so torn about this. Sorry, I'm very sorry for this. Anyway, you can see it, like this is the number that we're interested in, really. You can see the progression of these. And if you run the arc cosine of that, remember you can always set x to whatever you want. So we don't necessarily need that x, but now this is going to be expressing the angle between the two. So when they're aligned, you can see that the angle is 0, right? Look at, let's get that a better colored mouse again. Add the label to the green point. Ooh. The green point wouldn't give us like what we're interested in. Thank you for that, but the green point wouldn't give us the cosine value. It doesn't really matter all that much. We'll get to what it means in a second anyway. So you can see that when they are aligned, it's at 0. Then as the two come apart, let's hide that one. As the two come apart, you can see the value increasing, right? And in fact, you can do some things to show. So here's the thing, you can do inequalities as well. But nah, it won't work that way. Sorry. I was hoping to do something, but thinking about it doesn't work that way. So when you're here, you can see that it's expressing that there's an angle between the two that is pretty big. And if you look at that, that's 3.14, whatever. That is pi. That is 180 degrees in radians. Now, what happens, however, is that as we go this way, you see it's reducing. And that's because these operations are, let's say, unsigned. The result doesn't really have a sign. It's always positive. And this is a fundamental thing, a very, very fundamental thing about directions and why you have Euler angles and a number of other things. There's a number of myths floating around that, you know, if you use this or that thing, you can get plus 360, minus 360 between two directions. Like, say you have the two endpoints of a spine, the hip and the shoulders, and by some magic, in closed form, so without doing accumulations or anything tricky, you can rotate these. The animator can freely, in 3D space, you know, a bazillion degrees of freedom, rotate these, and somehow your spine has to magically figure out that this is 797 degrees and this one is 22 and produce two full spins down the spine. If you have two directions in word space that do not have other things in common, you just cannot do it. You need to give it other terms that express those spins. And that is where Euler angles, signed Euler angles, which is what the whole XYZ hierarchical order transforms, order rotations come into place. Because they allow you to express more than the half spin that this does. And if somebody knows of any magic by which, you know, a stateless closed form system can express those rotations, please let me know. Because I've heard people saying, oh, my spine does this and then. I know it doesn't. You can create that amount of spins. You need additional information compared to just the two directions, right? You can create that additional information if you track with a custom manipulator by, you know, giving a node a state, by tracking something many times, sampling it many times across frames so that you track increments that, because it's increment or decrement, that will allow you to sign what you have. Otherwise, this is an unsigned operation. So it took me a while, but I did get to the point where I wanted to get to before, you know, the last tiny part. All of these, I could have done it in 5 seconds, but all of this is to explain that this is what is happening here, right? Our foot roll mechanics. Did anybody even remember that we're talking about this? Talk about taking the long path. Our foot roll mechanics are using Euler angles, so they don't care. They're perfectly capable of expressing however many spins, because it's one angle over one plane, however many spins are required. And I am describing this by taking these 2 points, getting a vector between the two. So the mechanics themselves are basically taking this thing from its base position that might be here, and without a care in the word, they could do this a million times. But then from that, I extract 2 points, which are positions. Yeah, we'll talk about it. Sorry, chat question. We take those 2 positions, derive a vector, Then we say that we also have the z vector because we're resolving, like we're solving this in word space. And we're measuring the angle between the two. So when this is at its original position, it's going for this angle. Then as it crosses that boundary, right, that angle is going, whatever it is, 25 degrees, and it gets to 0. Then once it goes there, this is not the way we wish it to be, -7. This is the happy dream. The reality is that this is unsigned. This is saying it's 7, right? Which makes us very unhappy. But there's a few ways you can do this. You want something that allows you to find the sign, and that is where things like cross products and dot products and so on come in handy again. Because, and we said it before, and I think we have the tools to demonstrate it, we do have something where we can tell if two vectors are facing each other or not, right? So the dot product can tell us if this vector is going in the same direction of that, or if it's going in the opposite direction. That one works. And that's how we get more than 90 degrees, right? Because we know the numerical space fundamentally does 2 quadrants. So we can correctly represent the angle between 2 quadrants, which in one set of axes will actually also give us a sign. Because you know that this is plus plus, this is plus y and minus x, so this is minus plus, minus minus, plus minus, right? So if we add one more term in there, one more vector in here, as this vector goes across this boundary, if we also had another vector here, and we take the projection of these on that one, and I'm talking about projection because we don't need the angle, so we don't need to normalize a bunch of stuff. Again, if you were to write these to obtain a well-behaved derivation, fast code or whatever it is that you're interested in, that's pretty much what it boils down to. You only care about the sign. So if you take this vector that you already have and you look at its sign against these, right, which is going to be made by these two, then you will know that if that projection, even if it's scaled out to a basis that you're not interested in, so even if they're not normal, that both normal gives you the angle, one normal gives you the length, don't need it. You only care to know if it's like, is it positive or is it negative? That's the only thing that you need to answer, right? Then you're good. Then you know that you can take that and go like, if it's positive, I'm going to take +1. If it's negative, I'm going to take -1 and use that to sign the angle. Now, the other thing we're interested in is as we look at the vector, maybe we are able to do it right away. I don't know. So we have a Tarsi word direction. Plus minus average. Operation subtract. We can try right away. We could, yeah, so this is a 0 in the x, 352 in the y, and 16 in the z. So remember the vectors, just they only have a direction, okay? So all we care about is whether, in this case, the y is positive or negative. We don't even need to do anything more than that. And I think Duncan was suggesting that the other day. No, don't do that. Now I need to remap my mental model. Okay, Maya again. So is there a if condition? Yes. Now, first term 0, second term 1, equal, not equal, greater than. Now, so if the first term, which is going to be color if false R, So this is one of the things that Maya does. These are output attributes actually, but they make them writable, so they always appear like that, so that you can monitor them. Anyway, so if the dot product, sorry, I'm already running the dot product where I could probably just look at the vector, honestly. I was thinking like, what is going on here? Anyway, we're gonna keep that. Because it was giving me 3 vectors, so trying to think whether I want to give a good example or not. Because one of the two is when I was talking about using minimal derivations. One of the two, just the y of this vector will be enough, to be honest. Let's use the dot product for now, but we'll patch it again. So we go, if the first term is greater than 0, it means that the two are aligned. So if this has gone that way, right, it means it has a positive dot product with the y-axis. A positive dot product with the y-axis means that because of the way we're working out the angle, we want to negate it. And this is a bit backwards in a way, but we're working with what we have, then eventually we'll do better. I just had a thought just occurred to me, but I'm not gonna go there, sorry. So if it's positive, we want the sign to be what? Whatever. Okay. The sign to be negative, otherwise we want the sign to be positive. Now all we need to do is multiply that. So I think we're using an angular blend, additive DA, which means it will spare us from a unit conversion. So if I take input B, set the input to additive, set the operation to additive. So this is another thing that drives me nuts. It's showing me input B. It's not showing me input A because I don't know why. Maya and reasons and Maya. Anyway, so take that. Take the weight, come on, of what we have as the weight of A. Will that get us what we want? And take the output. It might not be right just yet, but whatever. Yeah, so we have an offset now, and that's okay. It's just we're negating at the wrong stage probably or whatever. But it doesn't matter. The thing that is interesting is that now if you look at the sign of it, the direction in which it progresses, it is now correct. Cool. Not gonna consider this fixed, but it is literally what I was trying to lead to. So there you go. It's kind of like as is often the case when what you expect to happen happens. It's somewhat anticlimactic as a conclusion, but that's it. That's what we wanted to get to. Show you how to use Desmos, show you how to do a few things like, drawing a circle or drawing vectors and points, and demonstrating as you move things around what is going to happen, visualize things. If you go through my math videos, or anybody else's for that matter, remember that most of the 3D stuff can be reduced to 2D operations just fine, because what you're doing is fundamentally making the Z part of it a 0, which just flattens out a bunch of things, or making it a something like a 001 anyway. Basically gives you an identity role for the Z. If you go over math anything, I suggest that the numerical part on paper is hard, but it's very useful. But at the same time, you have this happy medium, you have this, happy kind of like middle of the road place where you can do it in something like Desmos or Mathematica or some equivalent free application and learn a lot in the process. So this is what I wanted for the stream. Now there's a pile up the questions in chat. Is one that I'm going to try and answer if I can figure out exactly what they're talking about. But other than that, as far as I'm concerned, this is pretty much the end of it. I hope it was useful. Now, Question in chat is like, what are your thoughts using double cover like Casey laid out? I assume you mean Casey Muratori. I don't remember exactly what he's talking about with double cover. I mean, you can do things because quaternions are fundamentally vectors. They're in fact the ancestors of vectors as you know them now, which basically took away the imaginary part, forgot about the complex planes and the fact that the complex planes, you know, express rotations, and they were like, hey, we're gonna call them vectors because Hamilton called the real part of quaternions, he called them vector part. You can get over 180 if you low quads to have minus W. Yes, that is true. I'm still not entirely sure what we're talking about here. So the point is that if you allow quads to have a minus W and you turn them into affine quaternions, where you go like the minus W, you know, is gonna give me the sign so I know whether I'm going like this way or that way. You're kind of doing exactly what I'm talking about, which is you need another term to know what you're doing past the 180 degrees. And quaternions are a little bit peculiar in many regards, like even numerically, because they represent the concatenation of multiple rotations on several imaginary planes. So you have weird things like they need to spin a foot twice before they return to the original position. Operations are done by conjugation, and the conjugations of the quaternions look like multiplications in the real space. They have the peculiarities, but the moment you allow for negative W and you treat them kind of like affine quaternions, because I think you actually have to tweak how some of the operations work and you lose some of the quaternion properties, you're basically storing the sign. You're basically repurposing one bit inside your real quaternion to say this is the sign. Does that make sense? Do you get what I'm saying? Because your interpolation between the two will have to account for that sign. Now I will need to look at the video because maybe there's some numerical property I'm not aware of where by accident in the space of just normal quaternions, which is what you use 99.9% of the time anyway, and just in the operational, like in the transformational space of, you know, the conjugations that he uses and all of that, maybe that sign becomes a natural part of the operations, which makes it an even more desirable property. But you're still fundamentally doing plus 180 minus 180, which, if you want to be kind of retentive about it, is not exactly the same as doing a 360. When you will interpolate, you will have to do a little bit of work to account for the sign. And what I was saying that people so the plus 180 minus 180 is, there's a lot of ways to do it, especially if you have two axes basically. What I was talking about when I heard people saying, oh, mine can do plus 360 minus 360 on a spine, it's like, I don't believe you. It's not in closed form. If the not reliably in cross form without some serious edge cases. Do we have any other questions or feedback, in fact? Because this is kind of impromptu. It's like, all right, I'm gonna do a stream like this because I don't think Desmos gets demoed and shown enough. Let me reduce this because it's probably blinding. Now, next stream we're actually gonna go and fix a bunch of stuff. And hopefully it will make sense, because now you know what quadrants are and what the signs of the quadrants are and all of that. That's good to hear. I'm not surprised. Yeah, if you got about 75% of it, given how scatterbrained it was, that's remarkable. That's pretty good. Play with it. I guess this is, you know, an hour and 50 minutes of me saying, play with Desmos, do your own derivations. Like, if you have good tools, even if they're very simple numbers, in fact, grasping the nature of these being a bunch of very simple numbers, you know, working within the constraints of something this simple, it's amazing. Like, I love Desmos. It's amazing what they managed to get a web page to do. And yes, it's limited, but you know, turn that to your favor, because we're doing a lot of stuff here that people probably, if they have math beginners, if they have written it in an imperative form in their own APIs or whatever, they probably would have created vectors from other vectors and used the dot product or whatever, when all you need to do, especially if you're constrained on a plane, you know, if you're looking at just rolling something on the X, all you need to do is literally, you know, 1, 2, 3, 4 plus these 1, 5, 6 multiplications, which are super cheap, and 1 addition, and you're done. And these, you know, actually, if you're talking programming, this goes over the pipelines of the CPU really well, without a bunch of allocations everywhere. And then the R cosine is a transcendental that you kind of have to pay for. And that is how it relates to these. When you're looking to do things like rolls, keep it simple. If you know that you're operating on a plane, completely ignore the numbers that aren't changed. The last note I would have about it is, when you see the identity matrix, which you've talked about many, many times, it's the one that, don't need that transparent background. The identity matrix is the one in a 4x4 space, at least, is the one that looks like this. Oh, okay, sorry, what? Something going on, I don't know if you can see, I don't know, maybe my keyboard is interfering with my with my Wacom. It's driving me nuts. I don't know if you can see these cursory things. So in the case of an affine matrix, you know, if you know that this is the rotation part and this is the translation part, and you recognize these for the homogenization stuff, like if you recognize that in the subspace you're working in, like just rotations or maybe just 2 planes or whatever, on just 2 axes or 1 plane, if you recognize any of that, grab the raw numbers and use a subset of that operation. And the moment you need to look at something like this, learn to recognize identity, where you go, okay, the operation of rotating on X is rotating, the way Maya does it, is rotating around the x-axis, right? Where you go like, okay, I'm doing this, and that looks very bad, but you get the idea. So if you look at it, if you look at the actual numerical part of it, this is driving me, the tablet is driving me insane, but anyway, you can see that it's 1, 0, 0, 0, 0. So that is an identity operation, which means, and it's what you would expect. It means that when you're transforming by the x that way, I was keeping my fingers wrong, that was pretty bad. When you're doing that, anything that is sitting down the x-axis is going to be not changed. And that's great. Like anything that you do like that, any x part of anything that you're transforming to these new bases, the x part of it is going to remain unaltered. Learn to spot these things. The translation part is going to remain unaltered. All that is going to be changed are the y and z components of both the y and z rows / axes. Once you get used to it, you will basically start understanding some of the formalizations, and your intuition is still important. It's not like once you know the formalizations, you're out of the woods, but your intuition will step up, and that's how you learn the next hard thing. A lot of advanced maths is built on you having a very strong internalization of more basic maths, so that you can intuit in higher dimensions or greater levels of complexity and so on. Anyway, that's enough rambling. I hope this all makes sense. I'm actually quite happy I did it. I was jonesing to do it. When I was thinking like I want to show people some Desmos and explain like it's not that hard to do your own derivations. So if there are no further questions, I'm going to give it literally 1 minute and close it here, because this at this point is like 1 hour and 44 on the recording. No questions forthcoming, I guess. So thanks everybody for watching. Particularly thank you if you watch the stream. You guys keeping me company. and girls hopefully, but I don't think there's many coming to the streams these days. You know, you're making my day. This wouldn't be happening without you. All right, thanks everybody, and I'll see you the next time.